this video, we're going to finish this set of problems that we were looking at last time. I'll include a link down in the doobly-doo, the description of the video. What we were working on was this Cobb-Douglas utility function here, modified to where we have a minimum level, a subsistence level, D, of the good X, that we have to have in order to survive. So it's like a minimum requirement. And we went through, and in that video, we solved for the ordinary demand functions, Marshallian, Walrasian demand functions, whatever you want to call them. And we got a very similar result to what you would get with a normal Cobb-Douglas utility function, with the one modification that your income is kind of being treated as what I called in that video disposable income, because you're required to spend D times P. That is the minimum amount of X that you have to buy times the price of X. You have to spend that amount on the good X as your minimum requirement. And then what you do with the remainder of your income, after you subtract that DP off from your income, you split that the same way you do in a normal Cobb-Douglas situation, with the proportion A going towards good X and the proportion 1 minus A going toward good Y. And then we plugged those values back into the utility function to get the indirect utility function, which tells us how much utility you get as a function of the price of X, the price of Y, and the budget. And after plugging in and simplifying, we got this expression here. A to the A times 1 minus A to the 1 minus A divided by P to the A divided by Q, which is the price of good Y, raised to the 1 minus A, times this disposable income over here, this M minus DP. And we looked and saw, how does that compare over here in green to the normal indirect utility function we would get if we did not have the subsistence requirement for X. And we saw that these two equations look extremely similar here. The only difference is this minus DP. It's as if our income is being reduced by that minimum daily requirement of D of good X. And then we have the rest of our money to spend, and that's actually going to give us utility, which was a very interesting result. And what I said at the end of that video is there was a third problem in this set that I wanted to talk about. Now let's suppose that somebody taxes good X. How much income would we need to compensate the consumer? So we're talking about the compensating variation for the tax. So if we add, say, a 10% or 20% tax to the price P of good X, how would that affect the utility? And then what would we have to do to get this person back to the old utility level? So what I want to do here is two things. Derive the analytical solution and then run through a numerical example so we can see exactly how this is working. And at the end of the last video, I suggested that there are going to be two different parts that we need to think about when it comes to this compensating variation. Part number one is going to be the fact, let's zoom in here on this indirect utility function. If we see where our utility comes from, the first part that's going to be affected is when the price of good X goes up. That's going to reduce this thing I'm calling the disposable income, M minus DP. So that's going to be going down. The other impact is going to be that since the price in this part of the indirect utility function is going up, that's going to reduce our utility in a second way. So there are kind of two parts of this equation we see that are going to be impacted. How can we build in a proportional tax into a problem like this? There are a couple of different ways I can think about, but the easiest way is just to say, let's suppose there's a tax rate T, and what's going to happen is the price is P for good X. And when we go to actually buy it, they're adding a sales tax to it. So the price is now going to be P times 1 plus T. So for example, if the tax rate was 20%, now the price would get multiplied by 1 plus 0.2, so it would be P times 1.2. That's what I have in mind here when I'm talking about this multiplier 1 plus T. So let's look at what happens to this indirect utility function here. Let's call this equation 1 here, when we add in that tax. And all we have to do is say, well, the price of good X is going up. And what the indirect utility function allows us to do is to put in that new higher price here and here and see what happens. And then we can ask ourselves, what do we have to do to undo the effects of the tax on the utility? That's my strategy. Now, there are a lot of other ways we could probably go about this, but I think this is going to be the simplest path to getting us where we want to go. Here's equation, let's call it equation 2. We're just going to take the equation up there and say, okay, well, here's our new utility. Say U prime after the tax is going to be equal to, and I'm just going to write everything down from above. And I'm going to write the price of Q first here, 1 minus A, times. And now there's those two adjustments that we have to make. Now our disposable income is going to be M minus D times P times 1 plus T. The other adjustment is that the price in the bottom, that P, is also going to be times 1 plus T, right? But all of that gets raised to the A power. So when we compare these two equations, number 1 and number 2, we can see that really the difference is, let me move this P to the A over here. We can kind of separate the utility into two parts, right? Since everything is multiplied here, we have this part bracketed in blue on the left and the part in orange on the right. When we look at the same adjusted equation with the tax rate, we have this blue on the left and the orange on the right. So this helps us isolate exactly what changes are being made to the utility. All we have to really do is focus on the orange part on the right-hand side here and see how they are changing. And that's going to help us understand what we need to do to the person's income in order to make up for the 1 plus T here, adding that tax there and adding that tax in the bottom. Since both pieces have the blue, we just need to see how do we convert the orange here into the orange over here. I guess to help us talk about this, instead of making that orange, let's make that red, okay? So we want to convert the orange into the red. What would we have to do to the income that we have over here to spend to change it into this? And then at the same time, there's this part on the bottom here that we have to change to make it look like this. So here is my strategy to help us see the pieces a little more clearly. Let me rewrite the bottom of this equation. I'm going to distribute that A power, which I continue to accidentally write as an alpha. Let me distribute that A power to the P and the 1 plus T. So I'm just going to distribute it there. And so what we have is P to the A, 1 plus T to the A. This helps us see that one thing we're going to have to do in order to get from the orange expression to the red expression is we're going to have to multiply the top by 1 plus T to the A to get rid of that. All right, so we're going to have to get rid of that somehow. Another thing we're going to have to do is adjust this on the top. Instead of calling both of these things M, because we're talking about, with compensating variation, we're kind of asking the question, how much money should I give this person here, right? how much more money is technically the compensating variation, but we're asking what budget would I have to give somebody in this situation after the tax so that their utility is the same as over here. So let's call, instead of calling this M, let's call it B for budget. So how much money would we have to plug in over here for B in order to end up with the same result over here? The budget I would need for B is going to look like this. Now, why this amount? Well, let's plug it in and let's just see what happens. And now let's plug in this value for B and let's see what happens. It's basically going to undo the impact of the tax. And so the first thing we see is that these two items are going to cancel. The dp times 1 plus t is negative here. It's positive here. And then what we're left with is just the disposable income before the tax here multiplied times 1 plus t to the a power. And then we see the next thing that's going to cancel. 1 plus t to the a on the bottom, 1 plus t to the a on the top. And what that's going to leave us with is m minus dp over p to the a, which is exactly where we wanted to get to by adjusting the budget with the tax. So using this budget here would totally undo the effect of the tax and leave us with the same utility according to the indirect utility function here. I hope that makes sense. Now, if it doesn't, let's go through a numerical example. Well, before we do the numeric example, let's actually finish doing the analytics part. So what we've just shown is that this is the new budget. This B is the new budget that you would need with the tax to get you back to the old level of utility. The compensating variation is the increase or the change in the budget that you would need. So the compensating variation is going to be this new budget minus the old budget. So what we're going to have to do if we just want the compensating variation is to subtract m from that. And that's easy enough to see what that would look like. All right? So just the compensating variation is this expression for B minus m. So let's do a numeric example so we can see how this tax is going to affect the person and then how this new budget, how this compensating variation would undo the effects of the tax and give the person the same utility. So let's do a numeric example. Here's our utility function for this problem, and here are our Marshallian demands. Now let's do this example pre-tax and then we'll add the tax. So the parameters we need to specify here, let's suppose that A is 0.3, which means that 1 minus A is going to be 0.7, of course. Let's let our budget be 100. Let's let the starting price of good X be 5. The starting price of good Y be 10. And let's let this minimum daily requirement also be 10 units. So you need a minimum of 10 units of X to survive. And then when we do the tax rate, let's assume that the tax rate is 20% on good X, or 0.2. So pre-tax, using our demand functions we had, we're going to have X star equals 0.3 times 100 minus 10 times 5 over P, which is 5, plus 10. So we have to buy our 10 units of X, otherwise we can't survive. We're going to be spending 5 times $10 on those 10 units of X, which is going to cost $50. With our remaining money, that would be 100 minus the 50, we're going to spend 30% of that on good X. So the way this is going to work out is we're going to spend 30% of the remaining 50, 100 minus 50, on good X, and at $5 a piece, 0.3 times 50, we're going to be spending 15 of our disposable dollars on X, divided by 5 gives us 3, plus, don't forget this 10 that we have to have, so the amount of good X that we're going to be buying is 13. 15 over 5 is 3, plus 10, right? So, for good Y, similarly, but in a little more simple manner, we are going to have 1 minus A is 0.7 times our disposable income, which is 50, 100 minus the $50 we spend on that necessity, divided by the price, 10, and we're going to be spending $35 divided by 10 equals 3.5. So our Y star, 3.5 units. Now, how much utility are we going to be getting out of this? Well, we plug the 13 and the 3.5 back into our utility function over here. And we're going to be getting 13 minus 10 to the 0.3 times 3.5 to the 0.7, and our utility is going to end up being 3.342 approximately, if we round that off. So that's pre-tax. Now what's going to happen after we have the tax come in? Well, the price, instead of being $5, the price is now going to be 5 times 1 plus the tax rate, 0.2. And 5 times 1.2, the price including the tax, we could call that P star, is going to be $6 or 6 euros. So if we go and we plug that back into these equations, I'll just write down the results here. So what's going to happen is now that disposable income, after we buy the minimum daily requirement of good X, well, the minimum daily requirement is now going to take up $60 of our income instead of $50. So we're only going to have $40 in disposable income left after we buy the 10 that we have to have of X. When we take that disposable income, $40, we spend 30% of it on X, that's only going to leave us $12 to spend on our fun X, right? Not the minimum X that we have to have. And then that $12 divided by 6 means we're only going to be buying 12X, the 10 that we have to have, and then 2 that actually contribute towards utility. And again, because we only have $40 in disposable income to spend part of that on Y, we're going to spend the other 70% on Y, which means we're going to be spending $28 on Y. $28 divided by $10 means we can only afford 2.8 units of Y. And when we plug that back into our utility function, now we're going to get less utility, of course, and I calculate that to be about 2.5312, something like that. So our utility goes down, of course, after the tax. Now, what does this compensating variation say that we should do? Well, it says that if we want to get back to the old level of utility here, the 3.342, that instead of giving this person $100, we should give them this B. So let's plug in and see what this B turns out to be. $100 minus DP, so that's our old disposable income, so 10 times 5, times 1 plus t, 1.2, raised to the alpha, 0.3, plus dp, 10, times 5 times 1 plus t. So over on the right-hand side, we can see what that is. This is saying that, well, part of the amount of money we're going to need to get back to the old utility level is $50 times 1.2, or $60, right? So we're going to need the $60 that we need to buy our minimum daily requirement of X. Plus, and on this left side, this is going to compensate us for the fact that after we buy our minimum daily requirement of X, X is more expensive, and that's going to lower our utility as well. So this part on the left-hand side is compensating for that. And that's saying that we need 100 minus 50, or $50, times 1.2 raised to the 0.3, or 50 times 1.0562, which is $52.81, rounding off here, plus $60. So there are two parts to this new budget, and the compensating variation, again, is taking this amount of money, this new budget, which is going to be $112.81, that the compensating variation is that $112.81 minus the original budget, or $12.81. And the two parts of that compensating variation that I was talking about earlier, we can break into $10 is the additional money we need to buy the minimum daily requirement of X. And the other $2.81 is to make up for the fact that after we buy the minimum daily requirement, we have less ability to buy X then. Now let's just verify, last thing, let's actually verify that this is going to give us the same amount of utility. Otherwise, we haven't done anything, right? We don't really know that we've done the right thing here. So what we're going to do is we're going to plug in this budget and the tax rate and everything into our indirect utility function over here and make sure that we're getting the right amount of utility in this numerical example. And that target amount of utility that we want is this 3.342 that we got before the tax. We want to make sure that we get the same amount of utility after the tax with this new higher income. So let's plug everything in here. The new utility with this larger budget of $112.81 is going to be 0.3 raised to the 0.3 times 0.7 to the 0.7 over the price of good Y raised to the 0.7 times, let's put in the new higher budget here, $112.81 minus 10 units times 5 times 1.2, the 1 plus t, divided by, on the bottom, all multiplied times each other, of course, 5 times 1.2 raised to the 0.3. Let's plug all that into our calculators and see what we get. And sure enough, except for rounding error, we're getting the same thing as our target utility with this budget of $112.81, and our compensating variation, again, would be the $12.81 additional income we would have to give this person in order to make up for this 20% tax on good X. So I hope that was an interesting way to go about solving this problem that made sense to you. As always, if you have any questions or comments, please leave them in the comment section below. And if you have any other questions, talk to me. But other than that, this is Berkey Academy signing off, and I wish you the best of luck in trying to do long, hard math problems in your economic studies. Bye-bye now.